Welcome to our last chapter, chapter 9. And what we're doing now is we're looking at gas chemistry. And gas chemistry can be very interesting because we deal with pressure and volume in ways that we haven't ever before. So let's begin. It says I like this graphic. I don't usually do these overall graphics, but this is sort of like the amazing point of what's going on is that hot air balloons, they are like the quintessential gas chemistry in a way. So you heat up the air inside the balloon, okay? And as the temperature increases, because the pressure is exactly the same as the atmosphere is to the pressure inside the balloon, when the temperature increases, that means that the volume increases, but it changes the density and everything a little bit. And so basically the air inside the balloon has less mass. And so it's going to be able to rise up above, and it's very fun. Okay, so let's look at gas pressure. Gas pressure is the pressure, it's the force exerted on a given area. All right, and we're not going to get into pressure in general because we're mainly only going to be looking at gas pressure, which ends up being a little bit different. A barometer, with the picture I have here is an early barometer. And the reason it's different is because gas pressure is due to colliding objects rather than like a heavy elephant standing on a single place. A barometer is a device used to measure atmospheric pressure, and it was like a dish of mercury with a tall, thin tube inside it. And they found that the average atmospheric pressure at sea level would give a column height of 760 millimeters of mercury, or mmHg, millimeters of mercury. And that's still a unit that we use today. So what happens is that the atmospheric pressure is putting pressure here, okay? And the weight of the column, or the weight of the mercury, is putting pressure here. And when this downward force from gravity and the atmospheric force are the same, then that is basically what we say the pressure is. Now, as the atmospheric pressure increases, it pushes it farther up the tube. And then as the atmospheric pressure decreases, then it comes out of the tube. So the higher the atmospheric pressure, the higher the height of the mercury column. Okay, so the SI unit for pressure is the Pascal. And then here's a bunch of conversions that you need to know. There are 1,000 pascals in 1 kilopascal. Okay, and I also have that down here. 1 kPa is equal to 1,000 pascals. Pascal isn't a very useful way to measure pressure. So usually we might do kPas or millimeters of mercury or atmospheres. 1 atmosphere is the normal atmospheric pressure, and it's a standardized quantity where 1 atm is equal to 760 millimeters of mercury, or 760 torr. We don't usually use torr as often anymore because the torr is now slightly different than 760 millimeters of mercury, but you will see them to indicate the same thing. 1 atmosphere is also 101,325 pascals. 1 kilopascal is 1,000 pascals, and sometimes you will see pressure in bars. 1 bar is equal to 100 kPa. Okay, so let's just use a little bit of review time here. This is in the state of Maine. The lowest average pressure, 29.1 inches of mercury, occurs in June. Convert this to millimeters of mercury, atmospheres, and kilopascals. And it tells us here, just to review, that there's 2.5 centimeters in 1 inch. So before we do any conversions, the first thing we need to do is we need to get rid of these inches here. So we have 29.1 inches times 1 inch per 2.54 centimeters times 1 centimeter contains 10 millimeters. Okay, so we do 29.1 times 2.54 times 10, and that gives us that 29 inches is the same as, and I've got 3 significant figures here, so 739 millimeters. Okay, now I went from inches to millimeters. And so that inches is the same thing as your millimeters of mercury. So this is millimeters mercury here. And that's how you go between inches and millimeters of mercury. Okay, now what we need to do is we need to convert this to kPAs and to atmospheres. So what I'm going to do first is let's convert this to atmospheres. So we start out with 739 millimeters of mercury times, and I use this one right here. Okay. 760 millimeters of mercury per atmosphere. So then we do 739 divided by 760. The 760 is a defined quantity, so we don't have to worry about it in our significant figures, but we have 3. And so this becomes 739 divided by 760. Okay. So this becomes 0.972 atmospheres, all right? And that's how we show 3 significant figures, okay? And then they want this into kilopascals, okay? So what I'll do is I'll just keep going. I think that's easier than anything else. And 1 atmosphere we know is 101,325 pascals. But they want us to go all the way to kPAs here. And we know that there are 1,000 pascals in 1 kPa. And that is very difficult to see. Let me see if I can make that a little bit. 1,000 pascals and 1 kilopascal. Okay. 0.972 times 101,325 divided by 1,000. All right, and we end up with 98.5 kPAs, kilopascals. Okay. Okay. All right. All right, so we're relating temperature next. Volume, amount, temperature, the ideal gas law. So we're going to have a whole bunch of different things to look at here. At constant temperature and pressure, a gas expands uniformly to fill the container in which it is contained. So there's many different kinds of gases. We have, for starters, we have elemental gases. We have things like argon and helium are noble gases. And then we have our diatomic gases, hydrogen, nitrogen, oxygen, and others. You can also have gases as compounds, CO2, CO, H2O as a vapor, NH3. Okay, so there's a lot of different ways to form gases. Some of them are very light, some of them are actually reasonably heavy. All gases have the same dependence on 4 properties: volume, usually in liters, amount, which is actually N or number of moles, temperature, which is always in kelvins. Okay, so I want you to stop. I want you to make a note on the top of your paper, or make yourself a little Post-it note or a sign that says in chapter 9, your temperature must always be converted to kelvins every single time. All right, and then pressure. Pressure can be in atmospheres, millimeters of mercury, torr, pascals, kilopascals. This is the one that I noticed changes a fair amount. All right, so let's take a look at the effective temperature on gas pressure. All right, so here we have the hot plate is off. So let's say this is cold. When it's cold, the gas in here has low pressure because the molecules are kind of sluggish. As we start heating up our gas, we'll call this one warm, then the gas inside our sealed chamber starts to warm up. As it warms up, the air molecules start to move faster. As they move faster, they increase the collisions with each other in the side of the chamber, which increases the pressure. Okay. As we get even hotter, we end up with our gas molecules moving even quicker, which raises the temperature even farther. So as we increase our temperature, then we increase our pressure. And that's one example of how our gas laws are going to look. So for starters, the one I just showed you, we have a Montan's law or Gay-Lussac law. Gay-Lussac's law says that the pressure of a gas is directly proportional to its temperature and pressure. And what does it mean to be directly proportional? It means that pressure goes up as temperature goes up. It also means that pressure goes down as temperature goes down. And you can see that any direct relationship gives you this nice straight line. And P is equal to KT, where K is some constant here, is one way to describe Gay-Lussac's law, but we're not going to use that one very often, even though that's the definition. The one that you're going to use is P1 over T1 equal to P2 over T2. I'm going to teach you all the laws, and then we're going to do which law is this, because usually students don't have a problem using the laws, it's deciding which one to use. Our second one is Charles' law. Okay, Charles' law says that the volume of a gas is directly proportional to the temperature in Kelvin. Okay, so again, so that means that volume increases as temperature increases. Okay, at constant pressure and temperature. That was a really important one. I'm trying to go backwards. There we go. Okay, this is at constant volume and number of moles, the Gay-Lussac law. That means that volume and moles aren't changing. Okay, so it means not changing. And that's really big. These little gas laws only work when something is being held constant. Okay, so pressure and number of moles are constant. So that means volume goes up as temperature goes up, and that volume goes down as temperature goes down. Okay, and again, because it's a direct proportionality, we have a nice straight line, and the equation that you'll use is V1 over T1 equal to V2 over T2. And remember, temperature is always in kelvins on the other page as well. Our next law is Boyle's law, and this is the first one that's inversely proportional, and it talks about pressure and volume, and that's at constant temperature and amount, or temperature and number of moles. So temperature and number of moles aren't changing, and this inverse proportionality means that pressure increases as volume decreases, and that pressure decreases as volume increases, as long as your temperature and your number of moles, or your quantity, is not changing. And the equation for that will be P1 V1 is equal to P2 V2. All right, now we have a combined gas law, and the combined gas law takes the Gay-Lussac and Charles and Boyle and puts them all together. And that gives us, again, temperature must be in kelvins. The only thing held constant is the amount of the gas. And you get a variance like this, P1 V1 over T1 equal to P2 V2 over T2. The next one that we have here is Avogadro's law. And that says that the volume of a gas is directly proportional to the number of moles. So volume increases as number of moles increase, and volume decreases as number of moles decrease, and it's directly proportional again. So let's take a look real quick at what this means. So this here, this first equation says, and I'll come over here actually, 8. So what this is showing is showing 2 hydrogens plus 1 oxygen yields 2 waters. And the second one says that 1 hydrogen plus 1 chlorine yields 2 hydrochloric acid. And what Avogadro's law is saying is that you can look at what you have here. So if you have the first one, okay, now you could say the same thing for volume then, as you say for number of moles. And so what this is saying is that if you have 10 moles of hydrogen, then you need 5 moles of oxygen, right? And so we know that because that's our kind of our whole stoichiometry. But what we can also say that if you have, and I'll start this with if you have, okay? You can also say if you have 10 liters of hydrogen, then you need 5 liters of oxygen. So the same proportionality exists between moles and liters when everything is a gas. Okay. All right, and this leaves us with N1 over V1 equal to N2 over V2. Now we bring all of those gas laws together and we have the ideal gas law right here, PV equals nRT. And you're going to want to write these things down. The ideal gas constant R is 0.08206 liter atmosphere per mole Kelvin. What that means is that pressure is in atmospheres, volume is in liters, our quantity is in moles, our temperature is in kelvins, and then R is our ideal gas constant here. Now, these all have to be. So make sure that everything is in the right form before you try to do any math. All right, now we have come to our little game called Which Law Is This? It's so much more fun when we get to do it in class together, but now you just get to watch me play it by myself. All right, which law is this? I have to move things around my screen so I can see. All right, first it says a sample of helium gas at 23 degrees Celsius occupies 12.4 liters at 0.956 atmospheres. What volume, and notice I'm using the same thing, will it occupy at 1.2 liters? Okay, so this actually usually works a little better if I change color. So here, this one I'll make red, and the squiggly lines I'll make orange, and then we have blue. Okay, so you see here that we have 2 pressures, only 1 temperature, so that's not changing, and we have 2 volumes. We have a final volume that we're looking for and initial volume. All right, what that means is that we have pressure and volume changing, and everything else is constant. That means that we're using Boyle's law. And Boyle's law is P1 V1 equal to P2 V2. Okay, so we set that up and we say, okay, well, my initial pressure is 0.956 atmospheres. And my initial volume is 12.4 liters. And my final pressure is 1.2 atmospheres. And my final volume is what I'm looking for, V2. And so I would solve this. Go ahead and pull out your calculator. You're going to need it for everything. So you might as well do these problems with me. In order to solve for V2, I say 0.956 times 12.4 divided by 1.2. And I get a final volume equal to, and I look here and I see that I can have 3 significant figures. So it says 9.878666, and I can have 3. So this becomes 9.88 liters. And then I can check, and I can see that my my pressure went up, and it's Boyle's law, so my volume must go down. So as pressure goes up, volume goes down. Great. Okay, now let's take a look at another one. It says a balloon at constant pressure. Oh, well, that makes that easy. Constant pressure. So that'll help. It contains 1.3 liters of air at 24.7 degrees. And we're looking for a final volume. And it tells us that we're beginning at 24.7 degrees Celsius and we're ending at 78.5. So I can see my volume is changing, my temperature is changing, my pressure is constant. Okay, so that means that if we have volume and temperature changing, that we are dealing with Charles's law. Okay. And Charles's law says that volume increases as temperature increases, or vice versa. So we have V1 over T1 equal to V2 over T2. All right, now before I do anything else, the most important thing here is that I have to convert my temperatures. Okay, so here I can see that my T1 is equal to 24.7 degrees Celsius. And I have to add 273.15 to it to get my kelvins. So I have 24.7 plus 273.15. And so my T1 is equal to 297.85. And my T2 is equal to negative 78.5 plus 273.15 equals 194.65, and both of those are Kelvin. Okay, I'm just going to come over here and I'm going to remind everybody that our temperature in Kelvin is equal to our degrees Celsius plus 273.15, and our degrees Celsius, because sometimes this will come up, is equal to our temperature in Kelvin minus 273.15. All right, so my V1 is 1.3 liters and my T1 is 297.85 kelvins. My V2 is what I'm solving for, and my T2 is 194.65 kelvins. Okay. All right, now how do we solve this? So let's review our cross multiplication a little bit. You can draw a circle around these two on the diagonal, and we're going to times those and divide by what's left over. So let me show you how that works. V2 is equal to 1.3 times 194.65 divided by 297.85. Pull out your calculator. 1.3 times 194.65 divided by 297.85. And I get a final volume. I can have three significant figures, so it becomes 0.850. And if you're looking at it saying, no, it's not. Yeah, it is, because it goes like this, 0.84957. We're gonna have three significant figures. The 5 rounds up, and the only way to show that is 0.850. And we're in liters, and there we go. All right, let's take a look at another law. Okay, so this one says 2.45 moles of argon gas at constant temperature and pressure. Oh, they just told us constant temperature and pressure, and we're going from moles. We're changing moles and we're changing volume. So we've got volume and moles changing, constant temp and pressure. So that means that we're doing Avogadro's law. And Avogadro's law is N1 over V1 equal to N2 over V2. So when we set this up, we can say then that we have 2.54 moles over 89 liters is equal to 2.10 moles to our V2 that we're looking for. And this is how you do cross multiplication when you're looking for something in the denominator. You're still going to draw this cross multiplication like this. And you get V2 equal to 89 times 2.1 divided by 2.45. 89 times 2.1 divided by 2.45. And now I get a volume. I can have 3 significant figures, so the volume for this will be 76.3 liters. Okay. All right, now let's take another look here. An automobile tire at 23 degrees C with an internal volume of 25 liters is filled with air to a total pressure of 3.18. Determine the number of moles of air in the tire. Now the thing to notice here is that nothing is changing. Nothing is changing means that we have a static situation, and that's the ideal gas law. PV equals nRT. All right, now my pressure here is 3.18 atmospheres. And my volume is 25 liters. Equals my number of moles, so that's what I'm looking for, times my ideal gas constant R, which is always 0.08206 liter atmosphere per mole Kelvin, times my temperature. All right, well, my temperature is 23 degrees Celsius, so 23 plus 273.15 becomes 296.15. Okay, so then I will put that in here, 296.15, and I'll solve for N. And so we type in 3.18 times 25 divided by 0.08206, and then divided by 296.15. Okay, now if you've done this correctly, what you should get for your number of moles, 3 significant figures you can see again, is 3.27 moles. And it doesn't matter that air isn't constant. You don't have to find it that way. All right, more of these. I know there's so many of them because there's so many different laws. All right, so let's take a look here. It says, what is the pressure in a 304 liter tank that contains 5.670 kilograms of helium at 25 degrees Celsius? And again, the thing that we notice is that nothing is changing. And nothing is changing always means the ideal gas law, PV equals nRT. Now let's take a look here. Here we have our volume. But see how it says 5.670 kilograms of helium? That's not moles. That's an amount, but it's a mass. So then we need to start by setting up 5.670 kilograms of helium times, well, in 1 kilogram, there are 1,000 grams times, now the molar mass of helium, which if I look at my periodic table is listed at 4. Can't read it. Mine says 0.026 grams of helium per mole helium. Okay, so I do my calculation, 5.670 times 1,000 divided by 4.0026. And this tells me that I have 1,417, I can have 4 significant figures, 1,417 moles of helium. And then I can see here that I have 25 degrees Celsius. All right, So let's go ahead and change that. 25 plus 273.15 equals 290, whoops. It's easy to say something and write something else. 298.15 kelvins. So now I have temperature, volume, number of moles, and I'm looking for pressure. All right, so if I'm looking for pressure, pressure then becomes nRT over V, and we have 1,417 moles of helium times our ideal gas constant, 0.08206, times my temperature in Kelvin, 298.15, divided by the volume, 304 liters. Okay, now I type this into my calculator. And I get a pressure of 114 atmospheres. And that seems very, very high, but gases are often stored under great amounts of pressure just because it makes it easier to ship them. All right, and our last practice problem here says, at what temperature in degrees Celsius does 121 milliliters of carbon dioxide at 27 degrees Celsius and 1.05 atmospheres occupy a volume of 145 milliliters at a pressure of 1.4 atmospheres? So there's a whole bunch of stuff going on here. So first of all, it says at what temperature does, okay? Okay, so first of all, we have 121 milliliters of carbon dioxide at 27 degrees Celsius and 1.05 atmospheres. That's kind of the hard thing. We have all of this, so we're going to call these P1, V1, and T1. So my P1 here is 1.05 milliliters. Unless I'm dealing with the ideal gas law, I can leave this in oh, hang on. Not 1.05 mils, 1.05 atmospheres. There we go. I can leave this 121 milliliters in milliliters because this isn't going to be the ideal gas law. And temperature, we have 27 plus 273.15 gives us 300.15. Now we've got, I can see that we're going to have more of them. Okay, so it wants to know what temperature in degrees Celsius we're going to have. So that's going to be twofold. Occupy volume of what we have 145 milliliters. And we have 1.40 atmospheres. So sometimes when you've got a lot going on, it really helps to make a little list here. And now that you can see everything here, we know that this is the combined gas law, P1V1 over T1 equal to P2 V2 over T2, because everything is changing except my number of moles. So now I'm going to start putting all this in. So I have 1.05 times 121 divided by 300.15 equals our P2, 1.4 times our V2, 145, all over T2. Okay, well, we can set this up to cross multiply once again, and it works like this. So what that means is that my T2 is equal to 300.15 times 1.4 times 145 divided by 105 times 121. And you can put parentheses around these like so. All right, go ahead, take out your calculator, and let's go ahead and work through this. All right. So as you work through this, you should get a temperature that says 479.5785. I can only have 3 significant figures here. So this gives me 480 kelvins. But notice here that it says that it wants our temperature in degrees Celsius. What you have to do in that case is you have to say, okay, well, my degrees Celsius is equal to 480 minus, it would be minus 273.15, but we don't have any decimal points in this answer, so it just becomes minus 273. And we get 207 degrees Celsius. Okay. That's where we're going to take a little bit of a break, and I'll come back and we'll do another short video for the second part of chapter 9.